video continues the lesson from sections 2.4 and 2.5. And the previous two videos were very information heavy, and so if your head's spinning a little bit right now, I totally understand, okay? I'm hoping that what we're about to do here with the examples will kind of pull everything together for you, and you'll kind of see what the questions actually sound like that I'll be asking you about these functions. So in the first one, sketch a graph of y equals 0.5x on the coordinate plane at the right. So 0.5 is positive, okay? So I know which direction my line needs to point in. Oh, and I also know that it's a line because there's no exponent here. Okay, so that's the first thing I want to do is identify that this is going to be a linear function, okay? It's pointing up to the right because it's positive. And just as a sort of reference, and quite honestly, right now, you don't need to know this part, but just so that it rings a bell when we talk about it later. If my slope was exactly 1, it would hit like a perfect 45-degree angle through the middle here. Okay, so this would be with a k value of 1. And this number here, this 0.5, is going to control whether it slopes upward from there or downward from there. Gosh, that's really hard to do with a pen. But if this is a perfect 1, sloping up this way where it's steeper, that would be a number bigger than 1. And then sloping down this way would be something less than 1 if it's flatter than that pencil line. Okay? So 0.5 is smaller than 1, and so I would expect this to be a little bit flatter than what I drew there in pencil. But again, right now, I'm not really worrying about whether or not you know that piece of it. Okay, it's just good to get that practice because that's going to come up in the next chapter. These are the two things that I'd be looking for as far as a graph goes, is that you know that it's linear, that you know that it makes a line, and that you know that it slopes upward to the right, that it's pointing this way and not pointing downward. Okay? And then on this particular graph, when x approaches infinity, so as I walk out on the x-axis forever and ever and ever, where are my y values going? Well, they're going up forever and ever. So my y approaches infinity. Okay? And right now, I understand these questions probably aren't that interesting to you. I don't know that they'll ever be that interesting, but right now, it's always just infinity or negative infinity. All of the graphs we've talked about either go up forever or down forever. That's going to change when we get into some of the inverse variation stuff. So if you're wondering why that's even a big deal, it will get to be more important. Okay, and then example 2. Sketch a graph of y equals negative 3x squared. So here's what I would expect you to be able to pull from this. I know it's a parabola because it has an x squared in it. Okay. I know that it's going to point downward because the k is negative. And then kind of like with the slopes up here, that 3 tells you that it's actually going to hug the y-axis a little more. It's actually going to be skinnier than average. But again, right now you don't have to worry about that. That's just something that's going to come up down the road that I want to make sure that I kind of mentioned here. So it's going to point downward, and it's going to be a skinnier than average parabola. So it's going to look something like that. And again, here's where that comes from. If k is bigger than 1, it's going to be skinnier than average. And if k is less than 1, like a decimal or fraction, it's going to be wider than average. And again, I'm not stressing about these two things right now, but they're going to come up later in the year, and I just wanted to kind of touch on them right now. And then when I say skinnier or wider than average, average would be like a 1. Okay, if my k value was exactly a 1, my parabola would look more like this. It'd just be a little bit more open. Okay, but the blue one is the one you actually want down there as your answer. Okay, so now we haven't actually done one of these except for plucking points off of a graph, so you're really going to want to pay attention to this rate of change thing. Find the rate of change between x equals 1 and x equals 2. To find rate of change, the first thing I need is to turn both of these things into coordinates. So x equals 1 means I need to know what does 1 pair up with in this function. Well, that would be negative 3 times 1 squared. If you're going to put this in your calculator, I would type it in exactly like that, but it's really 1 squared, which is 1, times negative 3, so that's going to be negative 3. And then x equals 2, I would do negative 3 times 2 squared. That's 2 squared, which is 4, and then negative 3 times 4 is negative 12. Oh, ignore that, and hopefully no one comes barging in here. So 2 would match up with negative 12. So I took both of these and plugged them into the equation to find what y values they go along with. Okay? And then I'm just going to box this off. I'm going to use what looks like the slope equation or the slope formula. I'm doing y2 minus y1 over x2 minus x1. And we'll just call this point number 2 and this point number 1. It actually doesn't matter as long as you stay consistent. But okay, so to do that, gosh, I'm losing space here. y2 would be negative 12. y1 would be negative 3. So I'm doing negative 12 minus negative 3. Yes, I know we're going to have to fix that in a minute. Divided by x2 minus x1. So divided by 2 minus 1. Okay? Well, this is really negative 12 plus 3. So negative 12 plus 3 is negative 9. And then 2 minus 1 is just 1. And so then that comes out to be negative 9. And that right there is my answer. That's my rate of change. Okay? So what that's really saying is that between where x equals 1 and x equals 2, so if this is where x equals 1, if this is where x equals 2, our y values are dropping by about 9 for every one x value that there is. Okay, for every x value covered, we're dropping by 9 along the y-axis. Again, you don't have to be able to show that on a graph, but I just wanted to tie it back into the graph and make sure you understood. Okay, let's do the same thing between x equals 2 and x equals 3. Again, I'm going to plug both of these in and make them coordinates. Well, we already did that for x equals 2, so I know this coordinate's going to be 2, negative 12. When I plug in 3, that would be negative 3 times 3 squared. Well, 3 squared is 9, and negative 3 times 9 is negative 27. So this would be 3 and negative 27. Again, I just plugged the 3 into the x here. And now I'm going to go negative 27 minus negative 12. So I did this minus this over 3 minus 2. Well, this is really negative 27 plus 12, which is negative 15 over 1, which is just negative 15. And that right there would be my final answer for this question. So if I asked you for the rate of change, you would tell me negative 15. Okay? And again, that's saying that between 2 and 3, your y's are dropping by about 15 for every one step along the x-axis you take. So now this next question wants to know what would be the rate of change if you went all the way from x equals 1 to x equals 3. On average, how much are you losing? How much are you dropping on the y-axis every time you take one step over between these 2 points? Well, I already have both of these as coordinates. X equals 1 would be 1 comma negative 3, and x equals 3 would be 3 comma negative 27. So to set this one up, y2 minus y1, so negative 27 minus negative 3 over x2 minus x1, that's 3 minus 1. Negative 27 plus 3 is negative 24 over 2 gives me negative 12. So on average, between x equals 1 and x equals 3, every time I take one step along the x-axis, I would have to take 12 steps down along the y-axis to get to my next point. But notice that it's not the same, okay? No matter which pair I use, my rate of change changes. And the fact that it changes all the time is what differentiates this from a linear function. With a linear function, every single one of these would have the exact same answer, okay? No matter which 2 points you chose. Okay, and then just again looking back at our original blue graph here, When x approaches negative infinity, that's how you read that. So negative infinity would be this way. If you go out towards the negatives forever and ever, where is your graph going? Well, it's going down and down and down forever. So we would say y approaches negative infinity. Okay, that's about it for this one. I hope that answered at least some of the questions you may have had. If you do run into things on the homework that you're not sure about, we definitely will have some time on Friday to go back over that before we jump into graphs of inverse functions. But you're going to want to make sure you understand this rate of change thing before we get to inverse functions. So I would really put some good work into this today. Refer back to your notes if you need to when you get to the homework problems. Okay? Okay, best of luck to you, and I will see you Friday.